Greetings, everyone. Today we've got some more oscillations and simple harmonic motion that we're going to talk about. I've got one proof and 14 example problems, but they're all pretty quick. So I think that'll be actually quite interesting to look at this. Today we're going to be looking at a lot of example problems about a mass on a spring. So imagine this scenario. You've got a spring attached to a wall or something next to a frictionless surface, and we've got a mass on the end of the spring. We can take that mass and pull it out a little bit and then release it, and it will oscillate back and forth like that. If it's frictionless, it'll oscillate back and forth forever from position minus A to plus A. X is equal to negative A, X is equal to positive A. A is the amplitude, which is half the total distance that it's moving. It's kind of the radius, if you will. So negative A to positive A is where it's moving to and from, and it's doing that oscillating, it's doing that cyclically, that simple harmonic motion right there. To really do this justice, we need to find the angular frequency, or omega, for this mass on the spring. Remember, we did this with a pendulum. The angular frequency of a pendulum is the square root of g over L. We use this to come up with some interesting things about why tall people walk faster, which should be obvious, but it's actually still kind of neat to look at it mathematically. We also looked at how fast we're going to walk when we land on Mars and things like that. So, can we come up with something that looks like this? Some function of something is equal to the angular frequency of the mass on the spring, which is mostly just how fast it's going back and forth. Well, let's start by examining our equation for the acceleration of the mass on the spring. Now, I've got to say this before I go on. I know how to do this. This is just a pretty common proof. We haven't done a whole lot of proofs in my class. I think this is an interesting proof, and there's a lot of interesting techniques that you can learn from doing these kinds of proofs. The techniques you should be looking out for here is doing creative things with the equations that you already have and showing how they can relate to each other. So as we go forward with this, keep that in mind. Look at these equations and see how they can relate to other equations that we have already examined. Now the acceleration, we said last time, of anything moving in this kind of oscillation. Acceleration as a function of time is equal to the negative of the amplitude times the angular frequency squared times the cosine of angular frequency times time plus phi. This we got by taking the derivative of the position equation twice. Well, I want to find the maximum acceleration. Now, why am I finding the maximum acceleration? Because, well, I know how all this is going to turn out, and it's going to be very convenient for us to know the maximum acceleration of this. That's a technique that you can use in doing these kinds of proofs. If you don't know something, maybe you should look to maximize something or minimize something. That can help you constrain things later on. So what is the maximum acceleration of something with this function of acceleration? Well, it's going to be maximum when, what is this cosine term going to be when it's at its maximum? Yeah, cosine of omega t plus phi should be -1. We need it to be 1 because that's going to generally maximize things, but we need it to be negative in particular because we can get rid of that negative that way. Well, if we make this -1, then we can say that the maximum acceleration of a mass on a spring is going to be the amplitude of the oscillation times the angular frequency squared. Well, what else do we know about acceleration? Is there other equations that we can use to examine acceleration? Indeed there are. The net force on an object is equal to the mass of an object times its acceleration. Hypothetically, because F net is equal to ma, we can probably say, we can in fact say, that when we have the maximum amount of force on an object, if we have a force that varies up and down, or oscillates like this, then we can say that when the force is at a maximum, then the acceleration should be at a maximum. The maximum net force is equal to the mass of the object times the maximum acceleration of the object. In this case, the object is going to be the mass on the spring. Well, what are the forces going into this maximum net force for the mass on the spring? Do you know? Yeah, it should just be the force of the spring. The force of the spring is controlling everything that's going on in this problem, and that's equal to negative kx. The force of a spring is negative spring constant times position. Well, now we can combine this equation here, that the force on the spring is equal to negative kx, with this equation here, the net force is equal to ma. If the only force that matters is the spring force, then I can just take that, plug that in there, and I get this, that negative kx is equal to ma. All right, well, we've been talking about maximum accelerations and maximum forces. Is there anything we can do with that? Let's say that we want the acceleration to be a maximum. What is the position of the mass on the spring? What is x when acceleration is at its maximum? Think back to our diagram. Where will the mass be when the acceleration is at its maximum? And because we're using the positives and negatives, I want the acceleration to be the most positive that it could be, which would be the most this way that it could be. Where is the mass going to be when the acceleration is the most that way it can be? Well, it should happen when the mass is all the way over here, at negative a. When the mass has compressed the spring is really wanting to push that way as much as it can. And so when the mass has been shoved all the way over to negative a, then we should get the maximum amount of force in the positive direction. What does that mean here? That means that we can replace x with negative a. What does that do for us? Well, if I replace x with negative a, here I have it as positive a, but magnitudes, it's fine. Replace that there. The x goes to negative a. We get the negatives to cancel out, and now we have the spring constant times the amplitude of the oscillation is equal to the mass of the object times the maximum acceleration of the object. This is the maximum force. Spring constant times largest swing away from equilibrium. The amplitude is a measure of how far it gets from equilibrium. And the farther you get from equilibrium, the more spring force there is. So if the amplitude is the maximum amount, it makes sense that the maximum force is going to be spring constant times the maximum shift from equilibrium. That's equal to the mass times the maximum acceleration. Well, what can we do with that? This is one of those places that a physicist and an engineer in particular, anyone going into STEM, needs to get some experience in taking disparate equations that don't look like they should have much to do with each other and combining them together. And now we have these two that we can combine together. So I've got this Ka is equal to ma max, and I can combine that with this equation. Replace the a max with a omega squared. Got that. Well, what can we do there? We can cancel some amplitudes. And now we've got that the spring constant is equal to the mass times omega squared. And then it's not that big of a leap to notice that omega must be equal to the square root of the spring constant divided by the mass of the object on the spring. If you have a very weak spring, then you have a very small k, very small spring constant. A very weak spring is not going to oscillate anything very quickly. The object will not go back and forth very quickly if the spring constant is very small. If the mass is very large, for example, then even a strong spring is going to have a great deal of trouble making that go back and forth. So a very large mass there would also reduce the angular frequency of the oscillation of the mass on the spring. So this equation makes sense, and we are going to use this equation quite a bit now. I now have a rather stupidly large number of example problems for you. This kind of work really lends itself to having a lot of example problems because there's just so much you can do with it, especially now that we're at the end of the semester. There's just so many things that we can do in examining a physical system that it's time that we just do a lot of them and see what we can accomplish. Let's say that I gave you the equation of motion for an object that's in oscillation. The position of this object as a function of time is equal to 4.7 times the cosine of 3.8t minus 0.65, and the mass of this object is 2.1 kilograms. Using just this, and what else we've gone over in the very recent past, we're going to find the amplitude of the oscillation, the angular frequency of the oscillation, the phase angle, a function of velocity with respect to time, a function of acceleration with respect to time. We'll find the initial position, initial speed, initial acceleration, the spring constant. We will find the time and the velocity when the position of the object is at 3.1 meters. We'll find the kinetic energy of the object and the potential spring energy of the object when the object is at 3.1 meters, and we'll find the total mechanical energy of the system in the oscillation. That is not nothing. That's a lot of stuff, and it's actually kind of neat. I want you to write down this equation right here and the mass, and just save that somewhere nearby and handy so that we can go through all these example problems and I don't have to keep referring back to this equation right here. But let's start with these examples. We need to find the amplitude, angular frequency, and phase angle of this equation. Well, starting with that equation, how do you do that? Remember, from last time, that's the amplitude, that's the angular frequency, and that's the phase angle. Done. Okay, we've got the amplitude, the angular frequency, and the phase angle right there already. What's next? We need to find the velocity as a function of time and the acceleration as a function of time. Looking at that equation, can you find the velocity and acceleration as a function of time? Well, you just need to take the derivative and then take it again, and you got it. And we went over that last time. So the velocity ends up being negative 17.86 times the sine of 3.8t minus 0.65. Okay. And then the acceleration ends up being negative 67.87 times the cosine of 3.8t minus 0.65. As with any of these, you need to do more than just follow along with me. You need to actually be working on these before I can show you the answer. So please try to work on these problems before I can show you the answer. We need to now find the initial position, initial speed, and initial acceleration of this object. How are we going to do that? Yeah, we can just find the initial position by plugging in what for t? Yeah, plug in 0 for t, and we've got the initial position. How do we find the initial velocity? We plug in 0 for t in our velocity equation. How do we find the initial acceleration? We plug in negative 47 for t. That's a lie. It's 0 for t. Okay, good. What do we get? We get, oh, let's see. We get that the initial position in x is 3.74 meters. Now, when I was solving this just a little bit ago on my own, I forgot to tell my calculator to go to radians instead of degrees. And so when I did it in degrees, I got a ridiculous answer. And so I had to look at maybe why I got that ridiculous answer. Like, oh, I needed to change it to radians. So make sure that you have this interior bit, the stuff within the sine or cosine, make sure that that is always in radians. Why do we need that to be in radians? Because the 3.8 is in radians per second, and the negative 0.65 is in radians. We already have these things in radians, and so we need to tell our calculator that it's going to be in radians. So don't forget that. Velocity at t equals 0, we'll just plug that into the velocity, plug in 0 for t, and you get 10.81 meters per second. Acceleration, you get negative 54.0 meters per second squared. The next problem on our list is to find the spring constant. Now, what is the symbol for a spring constant? It's K. Can you look at a formula sheet and figure out how you're going to find K from anything else that you know? Well, we know from earlier this video, which this will also be on your formula sheet, that the angular frequency of a mass on a spring is equal to the square root of K over m. And I believe that we can use that to find the spring constant, the K, for this problem. Remember, that right there is omega, and I gave you the mass already. So we can just very quickly say our omega is equal to the square root of K over the mass, giving us a spring constant of 30.3 newtons per meter. For every meter that you stretch the spring, you get 30.3 newtons trying to pull it back. The next problem was to find the time and the velocity when the position is equal to 3.1 meters. Well, to find the velocity when the position is 3.1 meters, it makes sense to find the time first. So let's just find the time first. What time is it? How long has elapsed when the position is 3.1 meters? Now, of course, you know that this is oscillating back and forth. It is moving back and forth continuously. In doing so, it's going to be at 3.1 meters an infinite number of times if there's no friction, because it'll never slow down and stop. Let's just find the first time that it's at that position, at 3.1 meters. Well, when x is 3.1 meters, what is t? What is time? We can just take our equation and plug in that x is 3.1 meters. And then the rest is just our equation. Nothing new, nothing different. That's our regular equation. The rest of it is just solving for t. I want you to try solving for t on your own and see if you get what I get. Okay, well, I can divide both sides by 4.7. I can take the inverse cosine of both sides, and I can subtract off 0.65, then I can divide both sides by 3.8, and I find that the time is going to be 0.395 seconds. And as I said, that's just the first time that that will occur. What about finding the velocity? How are we going to do that? How will we find the velocity when x is at 3.1 meters? Well, we don't need to do anything special. We already know what time it's at 3.1 meters. So what are we going to do? We're just going to plug in 3.95 in for t, where t is, so this is our equation for velocity right there. We're going to plug in a time of 0.395 into our equation for velocity. So look at your equations and make sure that you see where we're going with that. And then it's just a matter of plugging and chugging. That is just right there, that's just calculator math. And you can see you get negative 13.43 meters per second at that time. We can do this for acceleration just as easily. What are we going to do for that? How are we going to solve it? For acceleration, we're just going to plug in the time again, 0.395. I put that decimal in the wrong place. There's the right place for the decimal, right there. 0.395, plug it into our equation for acceleration, and we get our acceleration right there, negative 44.7 meters per second squared. I think it's really interesting seeing how all these things all relate to each other. We've looked at oscillations from a perspective of kinematics a lot today. Can we look at oscillations as a matter of energy now? Let's find the kinetic energy of this object, of this mass, when it's at 3.1 meters, just like we were looking before. I'm always using the 3.1 meters. I just chose that number randomly because it is there, I guess. But let's find the kinetic energy when the position is 3.1 meters. How do you think we can do this? Knowing what we already know, we already have the velocity of the object when it's at 3.1 meters. Is there anything we can do with that in finding the kinetic energy when x is at 3.1 meters? The velocity there was negative 13.43 meters per second. Well, I hope you can see that finding the kinetic energy when you know the velocity is pretty straightforward. Kinetic energy is 1/2 mv squared. You plug in the numbers and you get an answer. And that's it. Sometimes you can be asked a completely off-the-wall kind of question, like what is the kinetic energy when this thing is at 3.1 meters? And to solve that, say you were just given that number, 3.1 meters, and you're given the mass and the equation of motion, this x of t thing. How do you take those things and turn it into a kinetic energy? Well, you know that if you've got a kinetic energy that you're working on, that requires a velocity somewhere, and it requires a mass. We've already got the mass, so we can scratch that off. The velocity we still need. If you're given a position function as a function of time, finding velocity shouldn't be too difficult. Just take the derivative of that, and you've got your equation for velocity. Now, we don't know what time we're looking at, and so to find that time, we need to plug in, oh, well, I want to find when x is 3.1 meters, so I need this to be 3.1 meters right there. And then 3.1 is equal to 4.7 cosine 3.8 t minus 0.65. Ugh. Okay. You see how many steps were involved there? There is a lot to take care of there. None of it individually was very difficult, but altogether it was a lot to keep track of. This is showing the importance of doing a lot of practice problems. If you have done a lot of practice problems, then you have encountered all of these individual questions separately. Now, critical thinking is taking those individual things and putting them together in one larger whole. That is a skill that I want everyone to get a little bit more experience with. You're at the age when you are learning the most about your own brain, and your brain is acquiring those critical thinking skills that you need as an engineer, as a scientist, whatever you're going to be, you need critical thinking. So giving you problems like this, telling you, hey, here's an equation and here's a mass, and I want you to figure out the kinetic energy when x is 3.1 meters. There's a lot going on there, but you can do it. Recognize you've got a mass, you need a velocity. You can find a velocity equation by taking the derivative of that, and then you can find a particular time when it'll be at that position using this equation, and then plugging that time into the velocity equation. It is a lot, but you can do it. Well, What about finding the spring energy when x is at 3.1 meters? How are we going to do that? This one is actually quite a bit simpler. We know that the spring potential energy is just equal to 1/2 kx squared. We found k already. We found that by taking the square root of k over m, setting that equal to omega, and we knew what omega was because that's omega right there in our equation. So this is another case where we've got a lot of things going on all at the same time, but if you can find k, even if it's through a whole bunch of steps, if you can find that and multiply by x, well, we're given x in this case, x squared, 1/2 kx squared, 145.6 joules. Great. Well, the last thing that I wanted to talk about was finding the total mechanical energy of this system. Remember what total mechanical energy is? It's the total kinetic plus total potential. Well, that's actually super easy right now. Total kinetic plus total potential. Okay, done. Total mechanical energy is just those two added up equals 335 joules. Done. That was simple. But is it consistent? Well, when the mass on the spring is all the way over at its maximum value, remember, imagine, the mass on the spring goes all the way over to the maximum position. X is equal to A. It's at its amplitude, at its maximum position. What is all the energy going to be when the spring is fully extended and the mass is as far out as it can be? All the energy should be spring potential energy. What is the kinetic energy when it's over as far as it can be? The kinetic energy has to be 0 because when it's over as far as it can be, it has to stop and then go back. So the kinetic energy is 0 because the velocity is 0 when it's all the way over. Well, if we plug in the amplitude for x, remember this is 1/2 kx squared, 1/2 kx squared. If it's at its amplitude and it's got no kinetic energy, you plug in amplitude of the maximum amplitude, 4.7 meters, times k, 30.3 newtons per meter, a squared times k times 1/2. You have no kinetic energy when it's at its maximum. You get the exact same number. You get 335 joules. Again, remember, the total mechanical energy does not change as you oscillate back and forth on the spring. We talked about that when we talked about energy originally. So this is just a neat example of how all of this connects back to effectively everything we've done this semester. There's a lot of critical thinking that you have to do here, but a lot of the time critical thinking is taking a large problem and breaking it up into a lot of small components and making sure that all the little components fit together just right. Build these skills. These skills will be important to you, not just on the test, not just on the final, not just in your next class. These skills, these critical thinking skills, will be important for the rest of your life in doing your jobs and understanding how to construct new things and how to analyze new data. That is what I want to teach you this semester, that critical thinking ability that we will all need going forward.